Before I get into this, I need to adjust the timing in that headline slightly because I want to be accurate with you. This wasn't detected 5 minutes ago. It was announced by NASA on July 13th of this year, a few weeks before this video, which in astronomy terms still counts as genuinely fresh, breaking research. Here's why it's worth your attention regardless of the exact timestamp. Astronomers have spent decades searching for something that should have been sitting in plain sight the entire time. Thousands of black holes, hiding inside one of the most heavily studied star clusters in the entire night sky, visible to the naked eye from Earth. They kept coming up empty. Then a research team went back through more than 20 years of Hubble's own archived data, combined it with brand new observations from James Webb, and finally caught one. A black hole so well hidden that its own discovery immediately overturned what an earlier team of scientists thought they'd already found in that exact same spot. This is the real story of Omega Cat BH2, the first stellar mass black hole ever confirmed inside the star cluster Omega Centauri. Why it took over 2 decades of accumulated data to actually find it, and why the black hole itself turned out to be strange enough to genuinely puzzle the astronomers who finally caught it. If you want accurate space reporting instead of manufactured urgency, subscribe now, because this specific hunt is only just getting started. Let's start with Omega Centauri itself, because understanding why astronomers were so determined to find a black hole hiding inside it requires understanding what makes this particular star cluster so unusual in the first place. Omega Centauri is a globular cluster, an extremely dense, roughly spherical collection of stars, all bound tightly together by their own combined gravity. It's genuinely massive as these things go, made up of roughly 10 million individual stars, gravitationally bound into a structure considerably older and denser than anything found in the relatively sparse neighborhood of our own sun. Sitting close enough to Earth and bright enough to be visible without a telescope under the right dark sky conditions, Omega Centauri has been observed and studied by astronomers for a very long time, making it one of the most thoroughly documented objects of its kind anywhere in our galaxy. That long observational history is exactly what made the missing black holes such a genuinely frustrating puzzle. Based on well-established models of how star clusters like this one evolve over billions of years, Omega Centauri should be absolutely riddled with black holes. The collapsed remnants left behind after the cluster's most massive stars burned through their fuel and exploded as supernovae over the course of the cluster's roughly 12 billion year history. Current theoretical models predict the cluster should contain something in the neighborhood of 10,000 individual stellar mass black holes, a genuinely enormous hidden population. And yet, despite years of dedicated searching using multiple different observational techniques, astronomers had never definitively confirmed even a single one, at least not until this specific discovery. If a story built on real, verified NASA reporting instead of manufactured urgency is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. It's worth understanding why finding these black holes turned out to be so genuinely difficult, because a black hole, by its very definition, doesn't emit any light of its own for a telescope to directly detect. Previous searches for stellar mass black holes within Omega Centauri relied primarily on 2 indirect methods, either the radial velocity technique, watching for a visible star's light to shift back and forth as an unseen companion's gravity tugs on it, or searching for radio and X-ray emissions produced when material actively falls into a black hole and heats up dramatically on its way in. Both of those methods work well under the right conditions, but they each carry real limitations, particularly for a black hole that isn't currently pulling in and heating up any surrounding material, meaning it would stay effectively invisible to that specific detection method no matter how carefully astronomers looked. The research team responsible for this new discovery, led by Matthew Whitaker at the University of Utah, took a fundamentally different approach instead, a technique called astrometry, which involves precisely measuring the tiny, gradual position changes of stars in the sky over long stretches of time. If a visible star is actually orbiting an invisible companion, its position on the sky will trace out a small, repeating pattern over time, a wobble caused by the gravitational pull of whatever it's orbiting, whether that companion happens to be another normal star, a neutron star, or a black hole. Detecting that kind of subtle, repeating positional wobble requires extraordinarily precise measurements sustained over a genuinely long observational baseline, exactly the kind of resource that only becomes available once a telescope has been reliably photographing the same patch of sky for years, or in this specific case, decades. If you found this technique as clever as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. This is where Hubble's own remarkable operational longevity actually became the deciding factor in making this discovery possible at all. Whitaker's team sifted through more than 20 years of Hubble's own archived observations of Omega Centauri, spanning all the way from 2002 to 2023, specifically searching for exactly this kind of subtle stellar wobble buried somewhere within that enormous accumulated data set. Once they identified a promising candidate, a single star whose position seemed to be shifting in a pattern consistent with an unseen, massive companion, they brought in additional, more recent observations gathered by the James Webb Space Telescope, using Webb's near-infrared instruments specifically to refine and sharpen the precision of their existing measurements even further. Whittaker described the resulting precision in fairly striking terms, noting that the team was measuring positional shifts down to a fraction of a single pixel on Hubble and Webb's own detectors, a level of accuracy he stated plainly would not have been achievable without both space telescopes working together on the same target. What that combined, decades-spanning dataset ultimately revealed was a star, sitting roughly 18,000 light-years away within the dense heart of Omega Centauri, orbiting something invisible, something massive enough that it could only reasonably be a black hole. The team designated their discovery Omega Cat BH2, officially confirming the first stellar mass black hole ever directly identified within this specific cluster, out of a theoretically predicted population numbering in the thousands. Here's where the story takes a genuinely interesting turn, because this wasn't actually the first time scientists believed they'd found something significant at this exact location within the cluster. A separate, earlier research team had previously studied the same binary system and proposed that the visible star's invisible companion was most likely a neutron star, the also extremely dense but distinctly different, collapsed remnant left behind by a slightly less massive category of exploded star than what typically produces a black hole. Whittaker's team, by expanding on that earlier Hubble dataset with their own additional archival measurements and the newly incorporated Webb data, was able to constrain the companion's actual mass with considerably greater precision than the original study had managed, and that improved precision changed the conclusion entirely. If you found this correction of an earlier scientific finding as interesting as I did, drop a comment and let me know. It genuinely helps me figure out what to cover next. Anil Seth, a co-author on the new study also at the University of Utah, laid out the specific numbers that settled the question. The visible star itself carries a mass of about 0.78 times our own sun's mass, a figure that had already been reasonably well established. What Whittaker's team's more precise measurements newly revealed was the mass of its invisible companion, calculated at approximately 4.46 times the mass of our sun, a figure decisively too heavy to be a neutron star, which have a well-established theoretical mass ceiling below that threshold. That specific number is what definitively reclassified the object from a candidate neutron star into a confirmed black hole. But Seth was quick to point out something else about that same mass figure, something that genuinely surprised the research team rather than simply confirming what they expected to find. A black hole with a mass of only 4.46 solar masses is considerably lighter than models generally predict should form within an environment like Omega Centauri specifically. That's because Omega Centauri is what astronomers call a metal-poor environment, meaning the stars within it formed relatively early in the universe's history, from primordial gas containing comparatively few of the heavier elements that later generations of stars, including our own sun, were built from. Existing theoretical models generally predict that stars forming in metal-poor environments like this one should produce more massive black holes when they eventually collapse, not lighter ones, making Omega Cat BH2's comparatively low mass a genuine puzzle rather than a straightforward confirmation of existing theory. Seth described the finding as both surprising and exciting, stating directly that the discovery demonstrates a metal-poor star really can produce a black hole of this specific size, and that researchers now need to figure out exactly how that happens, with this new detection providing real, concrete data for theorists specifically working on modeling that exact process. There's a second genuinely remarkable detail buried within this same discovery, separate from the mass puzzle, and it involves just how long it takes this particular star and its black hole companion to complete a single orbit around each other. Using the full decades-spanning dataset available to them, Whittaker's team calculated an orbital period of 94 years, meaning the visible star takes nearly a full century to complete one single loop around its black hole companion. That specific figure makes this the longest period black hole binary system ever confirmed anywhere, a genuinely significant record in its own right, and one that required Hubble's own multi-decade observational history to even become detectable, since a shorter observing baseline simply wouldn't have captured enough of the orbit's actual motion to confirm its existence at all. That unusually long orbital period also offers a genuine clue about how this specific system actually came together in the first place. Rather than forming together as a pair from the very beginning, the way many binary star systems do, researchers believe this particular star and black hole most likely found each other later, through what astronomers call dynamical formation, Essentially, a chance gravitational encounter within the incredibly dense, crowded environment at the heart of Omega Centauri, where stars and stellar remnants are packed closely enough together that these kinds of chance pairings can occur over sufficiently long timescales. That dynamic origin also comes with a genuinely poignant expiration date built directly into the physics of the system itself. Seth's team calculated that a loosely bound, dynamically formed system like this one, still shifting through a genuinely crowded stellar environment, likely won't survive longer than about 1 billion years before it eventually gets disrupted entirely by a close encounter with some other passing star or stellar remnant within the cluster. Compared to Omega Centauri's own age of roughly 12 billion years, that means this specific pairing represents a comparatively brief, transient relationship on the grand cosmic timescale of the cluster's own existence. A black hole and its stellar companion that found each other relatively recently and are destined eventually to be pulled apart again by the same crowded environment that brought them together. Seth also spoke directly to why finding even this single black hole carries significance, reaching well beyond simply confirming one more object exists where theory predicted it should. Understanding exactly how black holes form within dense environments like globular clusters and how they subsequently pair up into binary systems like this one matters enormously for interpreting an entirely different category of astronomical observation. Gravitational waves, the ripples in space-time itself produced when two extremely dense objects, black holes included, eventually spiral into each other and merge. Seth specifically noted that environments like Omega Centauri are considered among the leading candidate locations where exactly this kind of black hole merger and gravitational wave production is thought to actually occur, meaning better understanding how individual black hole binaries form and behave within clusters. Like this one, feeds directly into how scientists interpret the gravitational wave signals detected by entirely separate observatories here on Earth. It's also worth understanding that Omega Cat BH2 isn't actually the first hint of a black hole ever associated with Omega Centauri, which makes its confirmation as a stellar mass black hole specifically even more significant. Years earlier, a separate team using Hubble data had already found strong evidence for a considerably larger intermediate mass black hole sitting at the very center of the cluster, a category of black hole occupying a genuinely mysterious middle ground between the comparatively common stellar mass black holes formed from individual collapsing stars and the supermassive black holes found at the centers of entire galaxies. That central intermediate mass black hole and the newly confirmed Omega Cat BH2 represent two completely different populations of hidden objects within the same cluster. And finding both categories, one enormous and centrally located, the other comparatively small and drifting somewhere out within the cluster's dense stellar population, gives researchers a considerably fuller picture of just how much invisible mass this single ancient star cluster is actually holding on to. Tens of thousands of years after its founding, stars first began collapsing into stellar remnants. It's worth taking a moment to appreciate just how much this specific discovery actually depended on Hubble simply refusing to stop working. Hubble launched back in 1990, and by the time this particular research team began combing through its Omega Centauri archives, the telescope had already been continuously gathering data for well over 3 decades, making it possible to search for a stellar wobble subtle enough that it only becomes measurable across a baseline of 20+ years. No telescope launched more recently, including Webb itself, could have found this specific black hole entirely on its own, simply because none of them have existed long enough yet to build up that same multi-decade observational record. Webb's contribution here was genuinely essential too, sharpening the precision of the final measurements enough to confidently rule out the neutron star explanation, but it was Hubble's sheer, patient longevity that made the underlying 20-year baseline possible in the first place. A genuine testament to the scientific value of simply keeping a well-built telescope running for as long as it possibly can. It also helps to understand why globular clusters like Omega Centauri matter so much to astronomers in the first place, beyond simply being dense, visually striking collections of stars. Because the stars within a cluster like this one all formed at roughly the same time, from the same original cloud of gas, and have remained gravitationally bound together for essentially the entire history of the galaxy since, globular clusters function as something close to a frozen snapshot of a specific ancient era of star formation, preserved largely intact for astronomers to study billions of years later. Omega Centauri's own stars show a genuinely unusual range of ages and chemical compositions compared to most other globular clusters orbiting the Milky Way, leading some researchers to suspect it might actually be the stripped-down, surviving core of a much smaller galaxy that our own Milky Way consumed and absorbed at some point in the distant past, rather than a cluster that formed the more conventional way, all at once from a single collapsing cloud of gas. If that theory holds up, the black holes hidden within Omega Centauri, Omega Cat BH2 included, wouldn't just be relics of the cluster's own star formation history. they'd be surviving fragments of an entirely separate galaxy's history as well, quietly orbiting inside our own for billions of years after that smaller galaxy was absorbed and torn apart. It's worth understanding what comes next for this specific line of research, because Whittaker's team has been direct that Omega Cat BH2 represents a genuine starting point rather than a single isolated success. With the same combination of decades-deep Hubble archives and precise recent Webb observations now demonstrated to work, the team intends to continue searching Omega Centauri for additional hidden black hole binaries using the same basic technique, working to chip away at that theoretically predicted population of roughly 10,000 black holes still waiting to be individually confirmed. Whittaker also pointed toward an entirely new instrument that could dramatically accelerate that broader search going forward, NASA's Nancy Grace Roman Space Telescope, a mission specifically designed to image crowded stellar regions like the galaxy's own central bulge repeatedly and systematically, offering resolution comparable to Hubble's own, but across a considerably wider field of view, observed with a regular, consistent cadence specifically well-suited to catching exactly this kind of subtle, long-term stellar wobble across an enormous number of candidate stars simultaneously, rather than requiring researchers to painstakingly comb back through decades of archival data, one candidate system at a time the way this particular discovery required. It's also worth situating this discovery within Hubble's own broader, ongoing scientific output, because Omega Cat BH2 arrived during a genuinely active stretch for a telescope some people mistakenly assume has been fully overshadowed by Webb since Webb's launch. In the same general period surrounding this announcement, Hubble contributed to the discovery of a previously unknown category of starless, gas-rich dark matter cloud nicknamed Cloud 9, helped identify one of the darkest known galaxies ever observed, and captured detailed new imagery of star-forming regions and dying stars across the galaxy. More than 3 decades after its launch, and having contributed to well over 1.7 million individual observations across its operational lifetime, Hubble remains an active, genuinely productive research instrument in its own right, frequently working directly alongside Webb rather than having been quietly retired in its shadow. Exactly the kind of sustained, patient, decades-long operation that made a discovery like Omega Cat BH2 possible in the first place. There's a broader lesson worth carrying away from this specific story, too, one that goes beyond black holes and star clusters entirely. The single most important tool that actually made this discovery possible wasn't a brand new instrument or a dramatic technological leap. It was patience. More than 2 decades of a single, aging telescope quietly continuing to photograph the exact same patch of sky, accumulating a dataset nobody could have fully appreciated the value of back when those very first images were captured in 2002. Nobody observing Omega Centauri in the early 2000s could have known they were laying the groundwork for a discovery that wouldn't actually be confirmed for another 20-plus years. That's a genuinely different model of scientific progress than the kind most headlines tend to celebrate. Not a single dramatic breakthrough moment, but the slow, unglamorous accumulation of data, year after year, until enough of it had finally piled up to reveal something no single observation ever could have shown on its own. So, what does all of this actually add up to? Astronomers spent decades searching for the roughly 10,000 black holes theoretical models predict should be hiding inside the globular cluster Omega Centauri, and repeatedly came up empty using conventional detection methods. By combining more than 20 years of archived Hubble observations with fresh, high-precision data from the James Webb Space Telescope, a research team led by Matthew Whittaker finally confirmed the cluster's first stellar mass black hole, correcting an earlier study that had misidentified the same object as a neutron star, and revealing a genuinely strange, comparatively lightweight black hole locked into the longest period binary orbit ever recorded, a pairing that formed by chance within the cluster's crowded core and is itself destined to be torn apart again within the next billion years. It wasn't detected 5 minutes ago, but it represents exactly the kind of genuinely significant, actively unfolding scientific story that deserves real attention regardless of the precise moment it happened, the opening confirmation of a hidden population that astronomers are now actively working to fully uncover. If stories like this, the accurate version rather than manufactured urgency, are what you come here for, subscribe to this channel and turn on notifications. Because this specific search through Omega Centauri has genuinely only just begun. And there's a real chance the next discovery arrives considerably sooner than the last one did, especially once Roman joins Hubble and Webb in actively scanning the sky for exactly this kind of hidden, wobbling stellar system. Thanks for watching, and I'll see you in the next one.